This research focuses on multimodal large language models, MLLMs, and their potential for achieving generalized intelligence by integrating visual understanding into large language models. However, the substantial memory and computational demands of MLLMs hinder their widespread deployment. To address this, the authors explore efficient MLLMs from a distillation perspective, examining what matters for training small-scale MLLMs through knowledge distillation. The authors investigate four aspects of knowledge distillation between stronger teacher models and student models: feature embedding distillation, logit-level distillation, affinity-aware distillation, and data-driven knowledge distillation. Their empirical study reveals several interesting results, including that feature-level distillation can improve student results and work orthogonal to logit-level distillation, but is more sensitive to layer position in LLMs. Naive logit-level distillation works well, even better than specifically designed LLM distillation loss. Affinity-aware distillation losses do not work well in various cases, and data-driven knowledge distillation can improve student results by adding teacher-generated and instruction tuning data. The authors propose a simple yet efficient distillation framework, LLAVADI distillation, LLA versus ADI, which jointly distills features and logits, refined by teacher-generated data and instruction tuning data. They conduct extensive studies on various teacher and student baselines, demonstrating that LLA versus ADI can generalize to numerous teacher and student frameworks. The main contributions of this work include exploring the first detailed studies on MLLM distillation, showing that most existing LLM distillation methods cannot bring extra gains for MLLM, and demonstrating the superiority and efficiency of LLA versus ADI in multimodal datasets on various baselines. The research provides a comprehensive understanding of what matters for MLLM distillation, highlighting the importance of joint alignment for both tokens and logit alignment in teacher-student frameworks. The authors also demonstrate that even a 2.7B small-scale model can perform on par with larger models with 7B or 13B parameters by evaluating different benchmarks and proper strategy. Multimodal large language models, MLLMs, have been explored in various works, but existing methods face limitations. The mode-covering effect can result in hallucinations and low-quality outputs. Methods utilizing reverse KL divergence prioritize tokens where the teacher assigns high probabilities, preventing overestimation of low probability areas. However, these methods may also face mode-seeking issues, reducing diversity. Approaches aligning intermediate hidden states of student models with teacher models, such as GPT series, have been studied. LLAVA is a seminal work that feeds visual tokens into LLMs, enabling nuanced image information and intricate image-based reasoning. Mobile VLM and LLAVA-PHI explore efficient MLLMs, achieving stronger results in visual reasoning tasks. LLAVA's architecture consists of a vision encoder, projection layer, and large language model. The vision encoder outputs visual feature ZV for a given image XV. The projection layer converts visual feature ZV into language embedding HV. The LLM accepts instruction text token HQ and aligned visual feature HV as input. The LLAVA model uses two-stage training, pre-training and instruction fine-tuning. The pre-training stage involves 558K image text pairs filtered from CC3M. LLAVADI explores knowledge distillation on multimodal large language models, emphasizing multimodal models that produce outputs closely aligned with visual inputs. Various knowledge distillation approaches are proposed, including feature distillation, logit distillation, affinity distillation, and data-driven distillation. These approaches consist of a teacher model T and a student model S, where the student model has significantly fewer parameters than the teacher model. The student model undergoes two-stage training, employing mobile LLAMA as its LLM, containing 2.7B parameters. Layer-wise distillation is used to transfer knowledge from the teacher model to the student model. Feature embeddings distillation involves distilling feature embeddings H from intermediate transformer layers. The goal is to ensure the student model generates similar outputs as the teacher and handles information in a comparable way at hidden layers. The research paper presents a comprehensive approach to knowledge distillation for large language models, LLMs, in the context of multimodal learning. The authors introduced two primary methods for knowledge distillation: logit-level distillation and feature-level distillation. In logit-level distillation, the authors employ a softmax temperature-based KL distillation approach, where the student model is trained to align its logits with those of the teacher model. The authors also explore the use of Jensen-Shannon divergence, JSD, to balance the forward and reverse KL divergences. The feature-level distillation method involves aligning intermediate representations of the transformer layer between the teacher and student models. The authors find that aligning only the last layer yields better results than aligning the last two layers, which leads to significantly worse performance than the baseline. This is because the last layer contains high-level semantic information crucial for token classification. The authors also investigate the effectiveness of data-driven knowledge distillation, where the teacher model generates a large amount of contextual and domain-specific training data. The student model trained with these generated data samples can closely mimic the intricate understanding and cognitive abilities of the teacher model. The experiments are conducted on 6 datasets, including GQA, SQAI, VQAT, POPE, MMEP, and MMBDev. The teacher model uses the pre-trained CLIP VTL-14 with only 0.3b parameters as its visual encoder, while the student model employs the mobile LLAMA with 2.7b parameters as its large language model. The results indicate that the proposed knowledge distillation methods can improve the performance of the student model, especially in the fine-tuning stage. The findings suggest that aligning only the last layer yields better results than aligning the last two layers, and that aligning all tokens can lead to slight performance improvement than aligning only answer tokens. The authors also find that the MSE loss performs significantly worse than the baseline across all evaluation benchmarks. Overall, the proposed approach demonstrates the effectiveness of knowledge distillation in multimodal learning and provides insights into the design of distillation methods for LLMs. Here is a combined summary of pages 7 and 8 of the research paper. Knowledge distillation is explored for aligning logits using various methods, including KL divergence, logit standardization, and affinity-aware distillation. The results show that KL divergence consistently delivers superior or comparable results in all aspects, with the generalized JSD producing slightly improved results for VQAT and SQAI. Logit standardization also results in a significant decrease of MMEP while improving VQAT and SQA. However, aligning all token logits between the teacher and student models decreases performance for all aspects. Affinity-aware distillation is not effective for MLLMs, as the attention score or cosine similarity does not perform well. This is because affinity distillation is well suited for CLIP-like models, where the compatibility between visual and text features aligns better with contrastive loss. Data-driven knowledge distillation is also explored, where the instruction tuning dataset is regenerated using the teacher model or student model. The results show that data corrected by the teacher model performs well in VQAT, SQAI, and POPE, but has slightly declined in MMEP. The student model's limited capacity makes it challenging to replicate the teacher model's data distribution completely. Expanding the instruction tuning dataset to 2M improves model performance significantly. The paper also compares the proposed distillation strategy with Distill-BERT, an effective and efficient distillation method that reduces the size of a BERT model while retaining its language understanding capabilities. The results show that although Distill-BERT has almost twice the number of parameters as the proposed method, its performance is not as good. Overall, the findings suggest that KL divergence is effective for logit alignment, affinity-aware distillation is not suitable for MLLMs, and data-driven knowledge distillation can boost performance. The proposed method outperforms Distill-BERT in terms of performance. Distillation strategies for multimodal large language models, LLMs, are crucial for transferring capabilities from large to small models. A recent study compared various methods, including logit-level, feature-level distillation, and data-driven knowledge distillation. The results show that aligning classification logits and hidden embeddings of the final layer is effective. Additionally, data-driven knowledge distillation by generating answers using either teacher or student models demonstrates scalability. Table 5 presents a comparison of methods, including Distill-BERT, LLA versus ADI, and Mobile LLAMA, highlighting their performance on various benchmarks. Notably, the proposed distillation strategy trained models outperform the baseline model, even when using more powerful MO methods. For instance, MO ELLAVA 2.7b and Phi 2.7b yields slightly inferior results on GQA, SQAI, VQAT, and POPE. The study utilized logit level alignment by applying forward KL without norm standardization. Feature-level distillation matched all token representations of the final layer between teacher and student models. Data-driven knowledge distillation recreated the original 150K instruction tuning dataset using the teacher model, ensuring similarity. The performance evaluation in Table 6 compares current state-of-the-art SOTA methods on 6 vision language model (VLM) benchmarks. The results indicate that the proposed distillation strategy trained models outperform the baseline model, regardless of whether using 1.4b or 2.7b language models combined with the CLIP VTL-14 visual encoder. References to related studies are provided, including works on on-policy distillation of language models, visual language models for few-shot learning, and open-source frameworks for training large autoregressive vision language models. The references also include papers on language models as few-shot learners, plug-and-play inference acceleration for large vision language models, and Microsoft Cocoa captions. Overall, the study demonstrates the effectiveness of distillation strategies for multimodal LLMs, showcasing their potential for transferring capabilities from large to small models. Here is a combined summary of pages 11 and 12. The paper discusses various techniques for multimodal language models, including knowledge distillation, instruction tuning, and visual linguistic pre-training. The authors cite numerous studies that have explored these techniques, including Instruct-BLIP, Visual Dialogue, BERT, and Dyna-BERT. They also mention the importance of evaluating multimodal models using comprehensive benchmarks like ME and GQA. The paper highlights the significance of knowledge distillation in compressing large language models, referencing works such as Distill-BERT, Tiny-BERT, and structured knowledge distillation. The authors also discuss the role of layer-wise distillation and task-aware layer-wise distillation for language model compression. Furthermore, the paper explores the concept of visual instruction tuning, which involves fine-tuning language models on visual instructions. This technique has been shown to improve performance on various vision language tasks, as demonstrated in studies like visual instruction tuning and MFT coder. The authors also mention the importance of datasets like Obelix, Iconca, and Bench for evaluating multimodal models. They cite works that have utilized these datasets, including Learn to Explain and VigC. Additionally, the paper touches on the topic of object hallucination in large vision language models, referencing a study by Yifan Li et al. The authors also discuss the significance of thought chains for science question answering, as demonstrated in Learn to Explain. Finally, the paper references various other studies that have contributed to the development of multimodal language models, including ChatGPT, GPT-4, and Stanford Alpaca. The authors also mention the importance of evaluating multimodal models using comprehensive metrics, as demonstrated in works like Bench and GQA. The paper discusses the importance of teacher-student learning in improving fast segmentation models. It highlights the work by Kan Wu et al., who proposed a method called Tiny Clip, which utilizes clip distillation via affinity mimicking and weight inheritance. This approach has been shown to significantly enhance the performance of fast segmentation models. Additionally, the paper references various studies that have explored different techniques for improving segmentation models, such as self-training with noisy student and teacher-student learning. These methods have demonstrated their effectiveness in enhancing model performance and bridging the gap between teacher and student models. Moreover, the paper points out the limitations of current instruction tuning data generated by language models, which may contain inaccuracies or hallucinations. To address this issue, the authors propose regenerating the answer to each question using the teacher model, thereby distilling knowledge from the teacher to the student model through a data perspective. An example of a conversation generated by the teacher model is provided, showcasing how the teacher model can provide more accurate and detailed descriptions compared to the original instruction tuning data. This highlights the potential benefits of using teacher models to improve the quality and reliability of instruction tuning data. In conclusion, the paper emphasizes the importance of teacher-student learning and the need for more accurate instruction tuning data to enhance the performance of fast segmentation models. By leveraging techniques such as clip distillation and self-training with noisy student, researchers can bridge the gap between teacher and student models, leading to more efficient and effective segmentation models. Here is a combined summary of pages 15 and 16 of the research paper. The authors explore the scalability of their distillation strategies by conducting experiments on a combined dataset of 2 million instruction tuning samples, comprising various types of data such as VQA, region-level VQA, visual conversation, and caption data. This diverse dataset is structured in a dialogue format similar to LLAVA, with each type of data sampled equally. The dataset is composed of 10 distinct datasets, including BLIPLCS, visual dialogue, text VQA, VSR, VIGC, icon QA, SQA, COCO, SBU, and shared GPT-4V, with the number of image-text pairs ranging from 13K to 844K. The authors employ mobile LLAMA as their base language model, using the same set of hyperparameters as LLAVA. Notably, they do not employ any distillation strategy and solely train the projection layer during pre-training. The hyperparameters used include a batch size of 256 for pre-training and 128 for fine-tuning, a learning rate of 1E3 for pre-training and 2E5 for fine-tuning, with a cosine decay learning rate schedule and a learning rate warm-up ratio of 0.03. Despite achieving higher results than the baseline, the authors acknowledge that their results still fall short of their expectations and lag behind the teacher model's performance in most evaluation benchmarks. This highlights the need for further research and refinement to bridge this performance gap. The authors identify this as a limitation of their approach, emphasizing the need for continued exploration and improvement.